When students have learned to fluently add one digit to two digits and to fluently subtract one digit from two digits, they are ready to count multiples of 2, 3, 4, 6, 7, 8, and 9 in a way that will help them construct the meaning of multiplication. At this stage, students should easily be able to count by 2 beginning with any number. For example, 130, 132, 134, 136, 138, 140, 142, 144, 146, 148, 150. Let's look at the pattern of 2's. One thing that students should notice in this pattern is that every other column is empty. This is because 2 is an even number, and none of the multiples of 2 can be odd. Students should also notice patterns they have previously identified in the number grid. For example, each column has the same number of ones, and as we move down the rows in a column, we are adding a 10 each time until we get 10 tens, where we form 100 and start our count of tens again at 0. Counting by 2 is easy because of the regularity and simplicity of the pattern. 2, 4, 6, 8, 0. 2, 4, 6, 8, 0. 2, 4, 6, 8, 0. The pattern repeats after every 5 multiples because 5 2's make 10. Now let's count by 3. 3, 6, 9. Already we face a problem that we did not encounter when counting by 2. 10 is not a multiple of 3. When this happens, it is helpful to use the decomposition strategy we have learned. It takes 1 to make the next 10, and since we are counting by 3, we have 2 left over. Now let's use our knowledge of number composition to know that after 9 comes 12, 15, 18. Again, we will not end on a 10. This time we need 2 to get to the next 10, which means we will have 1 left over, and our knowledge of number composition tells us that that will be 21, 24, 27, 30. This time we did end on a 10, which we know means the pattern will repeat. 33, 36, 39, 42, 45, 48, 51, 54, 57, 60. Now we are back at a 10, so the pattern will start over. There is little to be gained by memorizing the multiples of the digits that make up the base 10 number system. However, there is much to be gained by learning to fluently count by those digits, starting with any multiple using decomposition and 10. This kind of strategic counting will help students to see patterns and relationships that are useful in constructing the meaning of multiplication. The first pattern that students typically notice in the multiples of 3 is what they may call the slanted or sideways pattern. This is a good opportunity to teach the mathematical term diagonal. Many students will notice that the value of ones decrease by 1 as you travel down a diagonal, whereas the value of the tens increase by 1 as you travel down a diagonal. These patterns actually exist because of the diagonal and the properties we have already noticed. If the value of the ones in each column is the same, then the value of the ones in the column to the left will be 1 less, and in the column to the right will be 1 more. Similarly, for the value of tens. The more interesting question is, why does the diagonal exist in the first place? Let's see if we can find a clue in the repetition of ones in the pattern. 3, 6, 9, 2, 5, 8, 1, 4, 7, 0. Notice that all 10 digits in the base 10 number system are used before the pattern begins to repeat. This is because none of the multiples of 3 is a 10 until we get to 30, which is 10 threes. 3 threes make 9, which is 1 less than 10. 6 threes make 18, which is 2 less than 20. 9 threes make 27, which is 3 less than 30. Then we get to 30 and the pattern repeats. This is why the multiples of 3 form a diagonal pattern. It is also why the multiples of 3 that are tens are multiples of 3 times 10. 3, 6, 9, 12, 15, and so on. Another pattern that students may notice in the multiples of 3 is the odd, even, odd, even, odd, even pattern. This is because 3 is an odd number, and adding an odd number to an odd number always produces an even number, whereas adding an odd number to an even number produces an odd number. Let's count by 4, starting at 100. 100, 104, 108. We need 2 to reach the next 10, and since we are counting by 4, we will have 2 left. So the next multiple of 4 will be 112, 116, 120, 124, 128. Notice that whenever we need to use decomposition, we are always 2 away from the next 10. So the next multiple of 4 will be 132, 136, 140, 144, 148. The pattern formed by multiples of 4 shares some similarities with the pattern formed by multiples of 2. 4 is also an even number, so none of its multiples are odd. As a result, the repetition of ones in the pattern 4, 8, 2, 6, 0, 4, 8, 2, 6, 0 includes only the even digits that make up the base 10 number system and repeats after every 5 multiples. This is because 5 fours make 20. What other patterns can you find in the multiples of 4? The multiples of 6 form a pattern that appears to be a mixture of the pattern formed by multiples of 2 and the pattern formed by multiples of 3. Can you figure out why? Here are a couple of hints. 6 is an even number, and 1 6 is 4 less than 10. 3 sixes make 18, which is 2 less than 20. 5 sixes make 30, which is a 10, and then the pattern repeats. Did you notice that 6 itself is 2 threes or 3 twos? 7 is the most difficult digit for most students to count by. Let's see if we can figure out why. 7, already we need to use decomposition. We need 3 to get to the next 10, and since we are counting by 7, we will have 4 left over. So the next multiple of 7 is 14. Again, we need to use decomposition. We need 6 to get to the next 10, and since we are counting by 7, we will have 1 left over, so the next multiple of 7 is 21. 28, we need 2 to get to the next 10, so we will have 5 left over. 35, this time we need 5 to get to the next 10, so we will have 2 left over. 42, 49, now we need 1 to get to the next 10, so we will have 6 left over. 56, now we need 4 to get to the next 10, so we will have 3 left over. 63, 70. Finally, we have reached a multiple of 7 that is a 10. Now the pattern repeats itself. You can see that 7 requires more strategic counting than any other digit we have encountered so far. This is because the pattern is the most irregular. Let's look at the repetition of ones. 7, 4, 1, 8, 5, 2, 9, 6, 3, 0, and now it repeats 7, 4, 1, 8, 5, 2, 9, 6, 3, 0, 7. There are some important similarities and differences between the pattern in multiples of 7 and that in multiples of 3. One similarity is that the pattern in multiples of 7 uses all 10 digits in the base 10 number system before it repeats itself. So far, only 3 and 7 have shown this pattern. Can you figure out why they have that in common? Here's a hint. 7 is 3 away from 10. One difference in the pattern of 3s and 7s is that 7 is a larger number, so more numbers must be skipped between multiples of 7. This is why more strategic counting is required to count by 7. By this point, most of the patterns in multiples of 8 should be pretty obvious. One thing that is important to notice is that 8 is 2 less than 10. 2 eighths make 16, which is 4 less than 20. 3 eighths make 24, which is 6 less than 30. 4 eighths make 32, which is 8 less than 40. 5 eighths make 40, and the pattern repeats. The multiples of 9 are often extremely revealing. Students who are attempting to memorize multiples typically struggle greatly with 9s. However, students who are using patterns and relationships with 10 will recognize that 9s have one of the simplest patterns of all. It is a pure diagonal pattern. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, 1, 2, 3, 4, 5, 6, 7, 8. This is because 9 is 1 less than 10. So 2 9s are 2 less than 20, 3 9s, 3 less than 30, 4 9s, 4 less than 40, 5 9s, 5 less than 50, 6 9s, 6 less than 60, 7 9s, 7 less than 70, 8 9s, 8 less than 80, 9 9s, 9 less than 90, and the pattern repeats.